Okay, good morning. Welcome to Introduction to Photonics. So far we have been actually looking at properties of photons in terms of the photon energy, we are looking at photon momentum, what does it mean to, what is the probability of finding a photon at a particular location, and related to that we were also looking at photon uncertainty. So what I would like to do today is, just see if we can gather all the things that we learned and see if we can solve problems, okay, related to photon optics. So let's take the example of let's say 1A, right. So you are told that you have a CW laser, right. You have a CW laser. So what does CW mean? CW is corresponding to continuous wave, okay, as opposed to the other type of laser which would be like a pulse laser, okay. So if it's emitting pulse laser, then pulses, you say it's a pulse laser. Otherwise, it's a continuous wave laser. Of course, we'll find that it's actually sort of a misnomer, because we talk about continuous wave as in continuously propagating as waves, but what we are actually going to look at is the photon properties of this laser, photon emitting properties of this laser. So you are told that this continuous wave laser has a wavelength of 0.2 microns, and it's emitting radiation which corresponds to 1 nanowatt of power, okay. Now what you are asked to figure out is, if you put a detector over here, then what is the rate at which photons fall on the detector. So what is the rate at which photons fall on the detector is what you're asked to figure out. So what we see is, in conventional wave optics, you deal with quantities in terms of power, energy density, power density, which is intensity, and so on. And what we will see in the corresponding photon picture is, we will talk about number of photons, we will talk about photon flux, which is actually what is asked here. What is the rate at which photons are arriving at a particular point? So that is what we call as photon flux. What is the photon flux density, okay, per unit area? What is the photon flux that we get at a particular point? So those are the quantities that we will start looking at, okay. So for example, here what you are asked is the photon flux. So photon flux, let's say you denote by this capital phi, is going to be given by the mean number of photons falling on the detector per unit time, okay. So n bar here corresponds to mean number of photons, right. So what is n bar? If you know the energy of light, okay, can we find what is the mean number of photons? So, mean number of photons n bar, how is it related to the energy? If your energy of your radiation is E or divided by h nu, which is the energy corresponding to a single photon, right. So, now we can if you are given power or energy, you can actually figure out that in terms of number of photons, okay. And of course, I say h nu, I may also use h nu bar. Where would I use that? If I have if I am given a broadband source, right, like what we were looking at yesterday, maybe your source has got multiple frequencies in it, and then you have a central frequency, right. That center frequency you may take as nu bar, okay. So, in this case you are given power, right, you are given optical power. How do you convert energy to power? What is the relationship? Power times the power integrated over time is energy, right. So, P times T divided by h nu. And so, now we need to find out h nu for the given laser. The laser is oscillating with 0.2 micron wavelength, right. So, we know that at lambda equal to 1 micron, what is the corresponding E? What did we see? 1.24 electron volt, right. So, you are asked to figure out the energy of a photon at lambda equal to 0.2 micron. What would this energy be? So, it is 5 times lower wavelength. So, the energy should be 5 times higher, right. So, 5 times 1.24, that would correspond to 6.2 electron volt, right. So, lambda at 0.2 micron is 6.2 electron volt, and if you convert that into joules, what do you multiply that with? 6.2 multiplied by 1.6 into 10 power minus 19 charge of an electron, and that would give roughly about 6.2 and 1.6 would be roughly about 10. So, that is about 10 power minus 18 joules, right. So, so if I am, what I am actually out to calculate is the photon flux. So, I go back to photon flux and I substitute instead of n bar, I substitute this expression. So, then what you get is essentially that the t in the numerator and denominator will cancel each other. So, what you get is this is going to be equal to the power divided by h nu, okay. Since I am having only one wavelength given, I can just take it as h nu. So, this is so the power that is given is 10 power minus 9, right, 1 nanowatt, and h nu we figured as 10 power minus 18, okay. So, that corresponds to 10 power 9 photons per second, right. So, the photon flux is 10 power 9 photons per second, which is corresponding to um, the power of 1 nanowatt at a wavelength of 0.2 microns. So, this is actually you can also say that this means that I have one photon arriving per nanosecond, right? One photon arriving per nanosecond on the average. So, this would be an interesting experiment. I was hoping I could give you a demo of this. We have done this before. So, you take a laser and you know, you take maybe a milliwatt power level laser, like what you guys have been working with for your demos, right? It's in the order of few milliwatts. So, you put an attenuator in front of it. You attenuate that to these power levels, 1 nanowatt power levels, and your detector, let's say it's a high speed detector. What I mean by that is it's capable of picking up light radiation at nanosecond time scale. Okay. You take that out of the detector and you convert that, the detector will give you a corresponding photocurrent which you convert to voltage, and you feed that voltage to a speaker. Okay. Now, what do you expect? You expect to hear a pop every nanosecond, right? So, you will basically, of course, you are not hearing at nanosecond time scale, you do not have that. So, what you will actually hear is this a continuous thing. So, you can actually listen to photons falling on the detector. So, that is actually a very beautiful experiment. We have done that before. I'll see if the TAs can arrange for that. It's not too difficult, but it just means that you need to find a high speed detector and connect it to a thing. So, you can listen to photons falling on the detector when you go to real low level of photons with high speed detector. Okay. That is when you believe, okay, all this is true. There are actually photons that are coming and falling on the detector. Anyway, so as far as what we were asked in this problem, we're just converting traditional quantities like power and energy into photons, in number of photons and photon density and so on. So, let us move on to another example. Example 1b, let us say, and this is actually related to something called laser assisted cataract surgery. So, we have actually started a company that makes fiber lasers. You don't know what a fiber laser is, maybe I'll come back and talk about that later on. But we make fiber lasers, and we make pulsed fiber lasers, and these fiber lasers are being looked upon. We work with one of the research institutes which is doing eye research as to whether this laser can be used to ablate tissue in the eye, okay, so that you can basically make a very precise incision in one of the tissue layers in the eye, and you can, through that you can do cataract surgery. Okay, so that is what laser assisted cataract surgery is all about. And in this case we use a pulse laser. Okay. So, the pulse laser, it's emitting pulse laser emitting 100 femtosecond pulses. What is a femtosecond? 10 power minus 15 seconds, right. So, it is pico, which is 10 power minus 12. So, 100 femtosecond pulses. At wavelength of 1.06 microns. Okay. Why that specific wavelength, we will come back and look at that later when we are discussing lasers, but let us say this is emitting these pulses at 1.06 microns, and you are told that you need 1 joule per centimeter square energy density to create a to basically punch a hole through the tissue layer. Okay. So, this is a process that is called photo disruption that you are doing, where you are actually cutting tissue with these pulse lasers. And why do you, so you can always use a high power laser and cut tissue. So, why do you want to use a very short pulse laser? Any idea? If you are continuously depositing energy on the tissue, it will be absorbed by the tissue, and then there is a heat that is generated. That heat will spread around the tissue, and it will end up charring the neighboring tissues also. There will be a lot of collateral damage that is happening. But if you are using 100 femtosecond pulses, what are you doing? You are packing a whole lot of photons within a very, very small duration. So, it goes and hits, and it does the work of getting absorbed, and then it's rupturing the tissue. But since it's all happening within that 100 femtosecond time scale, it doesn't, the heat actually builds up over millisecond time scales. So, if you are doing much shorter than that, there is very little collateral damage that is happening. So, you can get very precise cuts if you are using such short pulses. Okay. But you are told that you need 1 joule per centimeter square energy density. So, the question is, what is the corresponding photon flux density? Okay. So, that is what you are asked to figure out, and photon flux density, what do you think that corresponds to at a particular location? Let us say it is a small phi of r, would be what? Would be photon flux per unit area, right. So, that is what photon flux density is, and we know that from our discussion in the previous problem, we know that phi corresponds to n bar over T. Okay. So, you can substitute that over here, and what you are given is actually energy density, right. So, you can basically say this is going to be equal to n bar over T over A, right. But n bar over A, so I will keep 1 over T outside, right, and n bar over A can be expressed, n bar is in other words is basically E over h nu, right. So, you can write this as E over A times h nu, right. And what are you given? You are given energy density, which is E over A, right. and so if you substitute that, and then you can actually, and you also given this time. So based on that you can figure out. So let's just first of all figure out this quantity. So this is given by U over A, which is 1 joule per centimeter square, divided by h nu. H nu for a lambda of 1.06 micron, what do you think it would be? It's around something around 1.24 electron volt, right. So this is basically 1.24 electron volt, and then you convert that to joules, right. What do? Multiplied by 1.6 into 10 power minus 19, right. So that will be in joules, right. So if you do the math, you will probably get something in the order of 0.5 into 10 power 19, and this will be in terms of photons per centimeter square, right. So that will be the quantity here, and to get the photon flux density, you just substitute that into this other expression, which is basically you say 0.5 into 10 power 19 over the time. The interaction time here is 100 femtoseconds, right. So 100 into 10 power minus 15. So if you do the math, that will come out to be about 0.5 into 10 power 32 photons per second centimeter square. So that's the photon flux density that you need. Now that's actually sounds like a really large number, but you know what probably makes sense is that it's not the photon flux density that you are interested in. You are looking at the photon density. So you are actually you already packed so many photons. How many photons are you packing? You know, something the order of 10 power, I put it as 9, it should be 19 here, right. So that's 10 power 19 photons per centimeter square, but you're not doing a hole over a centimeter square area, right. That will essentially take out your eye completely. So you are actually doing holes, some micron holes, right. So when you do it in terms of micron square, right, it's maybe 100 micron square. So the number of photons is in the order of 10 power 12 photons, but that's still a huge number. You're talking about a trillion, so million, billion, trillion, a trillion photons, right. You're packing within one pulse, one bullet, okay, and you may actually require multiple pulses to do the precise cutting. So you are like, it's like a machine gun. It's just hitting with bullets, and these bullets are extremely powerful. I mean, you're talking about packing that many photons within a very short time scale. So these tissues have no chance. It will rupture in no time. But the key point here is, because it's all this interaction is happening within a very short time scale, the thermal buildup is very, very low. So you can get very precise cuts. Now it could be your eye, it could be this wooden table here, it could be a metallic part where you want to make a very precise incision, you want to actually do some patterns in a metal, some micro machining that you want to do in a metal, all of that you can do if you have femtosecond pulses. Okay. How we generate these femtosecond pulses, we will have to wait. I mean, there's still several weeks away. We'll come back and look at that in a little more detail. But if you have such a source, this is what you're dealing with. I'm just trying to give you a picture in terms of photons. Any questions before we move on? Okay, let's now look at another interesting example. Example 2, where we are looking at optical communication, right. So, in optical communication you have basically a transmitter, which is typically a laser based transmitter, and you are communicating information in bits, right. Let us say you are transmitting data at 10 gigabits per second, okay, and you are transmitting in on-off format. What does on-off format mean? One would correspond to the laser being on, you have a bunch of pulses and a bunch of photons, and off is the laser is off, right. So, you should not have any photons in the off condition, right. So, you are transmitting pulses like this, and if you are transmitting at 10 gigabits per second, your pulse period here the time period between two successive pulses is 1 over 10 gig, 10 gig is 10 power 9. So, 1 over 10 gig will be 100 picoseconds. So, within that 1 bit, which is in the order of 50 picoseconds, you either turn on or turn off the photons. Okay. What you are told is, in this case you have 20 photons, that is the mean photon number n bar, right, is 20 photons, and obviously with the off duration that would be 0 photons. Okay. So, that is what you have transmitted, and what you are asked to do is, in your receiver, right, what is the probability of finding 0 photons in a 1 bit. Why are we interested in finding that? Well, obviously, if you detect only 0 photons in a 1 bit, then that corresponds to an error. So, you want to find out what is the typical quantity by which you judge the performance of a communication system, a digital communication system, is this quantity called BER. BER is bit error rate. So, you want to look at the error rate that you are having in the communication, and typical bit error rates in communication, in optical communication, you try to look at 10 power minus 9. Okay. So, you want to achieve a BER of 10 power minus 9. Okay. 1 in a billion bit can be in error, but not more than that. Did you have a question? No. Okay. right. So, we are trying to achieve that, and to achieve that you need to understand what is the probability of finding 0 bits, 0 photons in a 1 bit. So, it is given that you are transmitting a mean number. So, the key point is this n bar is actually a mean number of photons of 20. What is the probability that you do not have any photons in that 1 bit at the receiver? You think if I am sending 20 photons, I mean something has got to be there. So, you would say that it is impossible that you will have 0 photons corresponding to that, but we will look into that little more detail now. The general misconception about light when we measure light is that we typically do what you do in the lab is actually you measure using a power meter, right, and the power meter essentially shows that it gives the power as a function of time. So, over a period of time you say the intensity is constant, right. So, that is what you are seeing, but what is the time scale with which the power meter is providing its value, doing the measurement? It is typically, it has got some integration time and all that. Millisecond is typical time scale that you have, right. In the millisecond time scale, everything looks constant. You get the perfect reading, 3.14, and so you put down the reading 3.14 milliwatt. But does that mean that you have a uniform stream of photons hitting that power meter? Actually not, because if you look at, if you actually do this, if you look at smaller sections in time, especially if you go down to kind of the time scales that we were projecting in the previous case, you will find that okay, in this time slot so many photons came, in this time slot so many photons came, in this time slot maybe a few more photons came, and maybe you would have a time slot where only a few photons came, and then another time slot where there is a much many more number of time slot that came, and so on, right. You get the picture. So, what I am trying to illustrate here is that even though your power may show up as uniform in millisecond time scales, if you go down to nanosecond, picosecond time scales, what you may actually find is that it is not uniform really. Okay. Why is this the case? I will just give you a clue at this point. We do not have a lot of lot of data points to say why, but I will just give you a clue here. We were looking at this picture of photon absorption and emission, and when we talked about a particular thing over here, there is a lifetime over here, right. So, there is a lifetime that it spends in the upper energy level before it comes down to the lower energy level. Now, that lifetime for rhodaman 6G is about 10 nanoseconds. Okay. In fact, we were trying to do a demo where we can measure this lifetime, but unfortunately that did not work out because we cannot generate pulses that are much faster than 10 nanoseconds with the equipment that we have with us. But nevertheless, the lifetime is approximately 10 nanoseconds, right, for rhodaman 6G. So, what does this lifetime mean? Does it mean that every electron that goes to the upper energy level, it spends exactly the 10 nanoseconds and then after that it emits? Not really. It actually, it's a probabilistic event. I was mentioning that this absorption is a probabilistic event, the emission also is a probabilistic event. So you can only tell in terms of some mean probability, right, over some mean time over which this emission happens. In fact, this lifetime is defined as, if you look at, if you send a pulse of light for the excitation, that you will have an emission corresponding to that which will be high initially because a large number of electrons are at the higher energy level, and then some of those electrons are starting to emit. So your fluorescence, if you look at the fluorescence as a function of time, you will see that it is actually coming down in an exponential manner, because there is a finite reservoir that is built in. With every photon that is emitted, that reservoir is getting emptied. So when you look at the rate at which the power is emitted as a function of time, it will come down exponentially, and the 1 over E point is what you figure out is the fluorescence lifetime. Okay. So what that says is that the photons are emitted continuously. Well, it's of course quantized wave packets that are emitted, but they are emitted at different times. So you cannot control, this is a quantum event, you cannot control it to say that it emits only at this particular picosecond, right. So it actually, you can track the envelope of that, but you cannot tell this photon is going to come at this particular time. So we are just building on that in saying that when you think about light emission, we think about light that is falling on me, you are detecting that in an integrated manner. You are not seeing photon by photon. If you go down to a picosecond time scale, you would probably see that these photons are coming at some random manner, it's emitted in some random time scale, right. So they are not coming uniformly, okay, that is the point. So your arrival statistics at the receiver, okay, that actually follows what is called a Poisson distribution. So since these photons are independently emitted, okay, the arrival status, you have what is called Poisson arrival statistics, okay, and it is actually not too difficult to derive this formula for Poisson arrival statistics. It is one of the example problems that is given in your textbook, but you can show that probability of finding n photons within time interval, in any given time interval, right, you denote as P of n. In this case, what you have done is you have sent a mean number of photons, n bar. Okay. So if you take the mean of all these small circles that I have drawn here, that would probably correspond to a mean of 6, okay, across all these things. So let us say you have sent 6 photons. What is the probability of finding 1 photon in one of these time slots, right. That's what we are tracking, and that for Poisson statistics works out to be n bar to the power of n exponential of minus n bar divided by n factorial. Okay. So, this is basically the Poisson statistics. So, let me actually select this and I will just okay. So, that is the probability that we have. Okay. Now, if I try to plot this, okay, then we may actually get a clear picture of what this means, what this Poisson arrival statistics mean. Oops. Right. So, here I have n and I'm plotting p of n 1 and let us say plot it in log scale. So, 0.1, 0.01 and so on, and n let us say 0, 5, 10, 15 and so on. Okay. Now, let us plot this function for n bar of 0.1. Okay. So, average within an interval is 0.1. So, you would say how can I express it as a fraction? Well, you cannot like tear the photon and say okay, this much is going here, that much is going there. No, it is not like that. You are basically saying that the probability of finding a photon over 10 consecutive time scales, this time intervals, is 1. So, it could appear in any one of those 10 time slots. Okay. So, that is what n bar of 0.1 means. But interestingly, if you plot this, you would find that you have a very good probability that you will find no photons in a given time slot, right. There is still a very good probability that you will find you will find one photon. There is a finite probability that you will find one photon in that time slot, or you could even have two photons in a time slot. There is a finite probability. However small the probability is, there is a probability. Why are we tracking this? Because our problem requires us to find 0 photons when you have a 1 bit. So, there you have n bar of 20, okay, and you are asked to figure out what is the probability that you find 0 photons in that time slot. So, if we work further, let me choose a different color, and if I say n bar of 1, that is going to look like this, right. I am just giving you a general perspective, do not pay too much attention to the specific numbers here. And if I go to n bar of 5, it is going to look like that, and similarly if I go to n bar of 10, and if I still go on to what we are looking for for n bar of 20 would have probably looked like this. So, of course, we have a scale here, the y scale, where we have only up to 0.01, but if you just extrapolate over here, you will find that it goes to a fairly low value. So, what we are actually trying to find out is this point over here. So, you have n bar of 20, right, that has been sent by the transmitter, that is the average that you have sent, but you could have a probability that 0 bits are there in that time slot. Okay, you have a finite probability. If you work out this expression over here, what you will find that this probability corresponds to 2 into 10 power minus 9. Okay. So, 2 times out of 10 power 9 bits, right. So, that is a billion bits. Okay. So, if you have collected 10 power 9 bits, then you may find that there are 2 bits where this sort of occurrence is happening. Okay. That seems like a very small number, but it is still significant in communications because of what? Because you are transmitting at 10 gigabits per second. So, within a second you might actually see 2 of these events. Okay. So that's the thing, but of course, like I say, it's relevant because of the high speed at which we are transmitting information. But the key point is, you cannot say that I am transmitting 10 photons in this slot and expect that all these slots are having only 10 photons. It could be 10, it could be 9, it could be 8, it could be 12, it could be 20, it could be 0. Each of these have a finite probability. Okay. So, when we are talking about photon streams, this is one of the important concepts that we need to understand, that you cannot control, you cannot time the photons so precisely. Okay. Just one quick thing before I end this, if I just go on to looking at for a Poisson distribution, if you look at the mean number of photons, that would correspond to, you have all these possibilities that it could be 0 or all the way to infinity, but the probability of those are weighted. So, n into p of n is the mean, and more importantly, if you look at the variance, so this is the mean and this is the variance. The variance for a Poisson distribution works out as infinity n minus n bar the whole square p of n, and if you compute that, interestingly what you find is that corresponds to n bar itself. So, the mean and the variance of a Poisson distribution are the same. Okay. So, that is an important aspect of Poisson distributions, and the consequence of that is, when you are looking at the signal to noise ratio, most of the communication applications, most of the practical applications of light, we are interested in the signal to noise ratio. So, the signal to noise ratio calculated in terms of photons, it corresponds to the square of the mean over the variance, which is the noise, right. So, in this case, that since you have a mean square divided by the variance, which is the mean, so your signal to noise ratio goes as mean on the photon. So, if you want to improve your signal to noise ratio, you want to have a larger mean number of photons, right. That is what it means as far as your communication application is concerned. Of course, that means that you want to flood your your time slots with photons, but it's not as simple as that, because in practical systems we find that beyond a certain number of photons, if you put into the medium starts behaving in a nonlinear fashion. Okay, that epsilon that we are talking about, the permittivity, which is the response of the medium for a given excitation or a given electromagnetic wave, right, that response, it's linear up to a certain number of photons. Beyond that, it is starting to behave non-linearly. So, you cannot extend this argument to a very large number of photons, because you will start hitting this nonlinear issues, and that's one of the major research areas in optical communication today. How do you prevent nonlinearity from happening in the optical communication system and still get very good signal to noise ratio. Okay. Okay, so we are out of time now, so let's stop at this, and what we are going into now is looking more closely at the absorption and emission of photons. How does that happen in different systems? What are the properties of those photons, and so on. So, we will going to build towards amplifiers, towards lasers, how to build lasers. That's what's coming up in the next few weeks. Okay. So, thank you.